Good morning students. In the previous video lecture on amines, we have studied some of the chemical properties of amines. They are basic character of amines. We have studied about alkylation, acylation, carbylamine reaction, which is a distinguishing test for primary amines. Then you have studied the reaction with nitrous acid, that is nothing but diazotization reaction. Now in today's video, we will discuss about the reactions. The remaining reactions, they are reaction with aryl sulfonyl chloride and electrophilic substitution reactions. The sixth reaction is reaction with aryl sulfonyl chloride. Aryl sulfonyl chloride is nothing but the benzene sulfonyl chloride, which is having formula C6H5SO2Cl. This is also known as Hensburg reagent. Structure, you can write it like this: Hensburg reagent C6H5SO2Cl. Okay, so this is the Hensburg reagent. This reagent is used to distinguish primary, secondary and tertiary amines. Okay, primary and secondary are giving the reaction, but tertiary does not undergo this particular reaction. So this is very important again for the examination, and even for 1 mark they'll ask what is Hensburg reagent. Hensburg reagent is benzene sulfonyl chloride. Its formula is C6H5SO2Cl. Okay, and when amines reacts with benzene sulfonyl chloride, it gives respective sulfonamides. When amines are treated with benzene sulfonyl chloride, there is a formation of respective sulfonamides. Sulfonamides are formed as a product. We will see the examples now with respect to primary and secondary amines. We will take an example of primary amine here, that is ethylamine. I will take as an example. So what happens when we take ethylamine? When benzene sulfonyl chloride is treated with benzene sulfonyl chloride is SO2Cl. So when it is treated with ethylamine is C2H5NH2. This is primary amine. So when benzene sulfonyl chloride is treated with ethylamine or ethanamine, what happens? You can see there is a hydrogen and here we have a Cl. So this combines and goes out as HCl. So what you get as a product? Now just write benzene SO2 group as it is. Now this goes out as HCl. So now sulfur links with the nitrogen with one hydrogen and C2H5 plus HCl. So this is N-ethyl benzene sulfonamide. N-ethyl benzene sulfonamide. Okay, and this is soluble in a base. Okay, it is acidic in nature. Because of this proton, it is acidic in nature, so it is soluble in the alkali. It is soluble in the base. Okay, the hydrogen attached to the nitrogen in the sulfonamide is strongly acidic. That is due to the presence of strong electron withdrawing group. The sulfonyl group is electron withdrawing group. So because of this nature, electron withdrawing nature of this group, this hydrogen will be acidic proton. This is acidic proton. Okay, and this makes this whole compound as acidic, and because of this acidic nature only, it is soluble in the alkali. Understood? The primary amine is treated with benzene sulfonyl chloride, results in the formation of N-substituted benzene sulfonyl amine. So here this is soluble in alkali because of its acidic nature. Why it is acidic? The hydrogen attached to the nitrogen is having acidic nature, and that is because of the presence of strong electron withdrawing sulfonyl group. Okay, So this is soluble in alkali. If I take an example of secondary amine, what happens? See, the reagent remains same, that is benzene sulfonyl chloride. So if I take benzene sulfonyl chloride, when it is treated with N-diethyl amine or N-ethyl ethanamine, this is secondary amine. Okay, so when there is a reaction between these two, what happens? H and Cl goes out as HCl. So there is a formation of benzene with the sulfonyl group connects to the nitrogen, which is having two ethyl groups. HCl is a byproduct. So this is N-diethyl benzene sulfonamide. Okay, so this is the reaction of Hensburg reagent with the secondary amine. There is a formation of N-disubstituted benzene sulfonamide, and here you can observe that it is not having any hydrogen on the nitrogen. So both are alkyl groups. There is no hydrogen here, so there is no acidic proton present on the nitrogen atom, because of which it is not acidic in nature, so it is insoluble in alkali. Whereas in first case, what happened? In first case, there was a acidic proton. Because of its acidic nature, it was soluble in the alkali. But here the product is not acidic in nature, it is insoluble in alkali. Correct? So because of the absence of acidic proton, there is no hydrogen on the nitrogen. Whereas in case of tertiary amine, if we consider the tertiary amine, there is no reaction with the Hensburg reagent. And the reason is, what will be the reason? Hensburg reagent reacts only when there is a hydrogen availability on the amine. So as in case of tertiary amine means nitrogen will be connected to 3 alkyl groups. So in this case, all the groups are alkyl groups. So to react with the benzene sulfonyl chloride, there should be hydrogen, so that it goes out as it combines by the liberation of HCl. So as there is absence of hydrogen atom, it is not showing any reaction with the Hensburg reagent. So as all the 3 different amines show different way of reaction with the Hensburg reagent, Hensburg reagent is used to distinguish primary, secondary and tertiary amine. So you might have asked in the examination, name the reagent which is used to distinguish between primary, secondary and tertiary amine, and the answer is Hensburg reagent, where primary reacts to form a product which is soluble in alkali, secondary reacts with the Hensburg reagent to form insoluble product which is insoluble in alkali, whereas tertiary amine does not undergo the reaction. Okay, so this is how the different amines are distinguished by using Hensburg reagent, that is C6H5SO2Cl. The next chemical property of amines is electrophilic substitution reactions. In addition to the reactions of amino group, aromatic amines are also undergoing electrophilic substitution reactions, and that is because of the presence of aromatic ring. You know that aniline is showing the following resonating structures, right? So nitrogen will be carrying lone pair of electron which is in conjugation with the benzene ring. So that's why there is an interaction between these lone pair and this pi system. So there you can observe the resonance effect. So the lone pair of electrons are given to the bond. Next the bond is shifted on the carbon, so that the negative charge comes at the ortho position, and you will get your first resonating structure like this. There is a double bond between carbon and nitrogen. Nitrogen carries positive charge, and here we get the negative charge. So now the charge is shifted on the bond is shifted on the carbon. So now the negative charge comes at the para position, right? So the remaining things as it is. Okay. Now again the next resonating structure can be written like this. I hope you all know how to write the resonating structures. Right? So, like this, you can write the resonance structures for aniline. Total 5 resonating structures are there for aniline. So, from these resonating structures, you can observe that because of the presence of 3 pi bonds, that is 6 pi electrons, benzene ring is electron rich center. That's why it shows electrophilic substitution reaction. When the NH2 group is attached to the benzene ring, what happens? The electron density in the system will be varied, and that is how it is explained by the resonance structures. And you can observe in these resonating structures that the negative charge is localized at ortho and para position. You can observe that the negative charge is here at ortho, at para and at ortho. So that means NH2 group, when NH2 group is attached to the benzene ring, the electron density is more at ortho and para position. So whenever we do electrophilic substitution reaction, the incoming electrophile goes and attacks ortho and para position. So you can tell that NH2 group is ortho-para directing group. It directs the incoming electrophile to attack at ortho and para position. And also it is highly activating ortho-para directing group, highly activating the benzene ring towards electrophilic substitution reaction. The term highly activating is used because you know that the first step in the electrophilic substitution reaction is generation of electrophile. Second step is attack of electrophile to form a carbocation. That carbocation is stabilized by the resonance. So, in case of aniline, when I'll take an example of aniline here. Sorry. If I take an example of some electrophile is going to attack the aniline. Okay. So here there is a formation of, when this electrophile attacks the benzene, this aniline at ortho position, you will get this kind of carbocation, correct? So the positive charge will be here, NH2 group. Okay. So like this you will get one of the it may be one of the resonating structure, or this may be the species after the attack of electrophile. This will be the carbocation form. So here you observe that the lone pair of electrons are present on the nitrogen. So the positive charge is present on the next carbon. So in this case, there is a shift of these bonds and the carbocation will be stabilized like this. See, I'll write the normal resonating structure. The positive charge comes here and this is shifted here. So bond comes here like this. It will be shifted to get the stability. Okay. But with these resonating structures, another possibility is, as the lone pair of electron is present on the same carbon which is having the positive charge, so we may get another resonance structure of this manner. That is, the positive charge is taken by nitrogen, the lone pair of electron is given to the bond. So there is a chance of getting this another type of resonating structure. So because of this resonance structure, the carbocation formed, which is an intermediate in the electrophilic substitution reaction, is further undergoing stabilization because of the extended resonance. Okay, so because of this kind of resonance effect, this is highly activating ortho-para directing group. It directs the incoming electrophile to go at ortho and para position, and it highly activates the benzene ring towards electrophilic substitution reaction. So that's why, for this reason only, whenever aniline is subjected for electrophilic substitution reaction, what happens? The electrophile goes and attacks all the 3 electron dense positions, that is ortho and para position, and you are getting tri-substituted aniline as a product. Like this, electrophile goes and attacks all the three positions which are having more electron density, and we get tri-substituted aniline as a product. This is because of the higher activity of NH2 group. To get the single substituted aniline, we have to reduce the activity of NH2 group by modifying it, and that modification is done by converting NH2 group into NHCOCH3 group, which is also ortho-para directing, but comparatively the activity is less than that of NH2 group. This can be done, this modification is done by the acylation of NH2 group. So whenever we need mono-substituted aniline, first we have to do acylation of NH2 group so that the reactivity is reduced. After that, the electrophilic substitution is done so that we get substitution only at the single position. So to get the mono-substituted aniline as a product, we have to convert NH2 group into NHCOCH3. That is, we have to do acylation so that the activity of NH2 group is reduced, and this is done by acylation. So as acylation, or this acyl group, COCH3 group, is electron withdrawing in nature, when we do acylation, the COCH3 group is attached to the nitrogen. So now the lone pair of electron is not only available for the donation in the benzene ring, but because of the presence of this acyl group, even these electrons are withdrawn towards the acyl group, as it is electron withdrawing in nature. Because of the presence of this carbonyl carbon, there is an interaction between the lone pair of electrons present on nitrogen and this carbonyl carbon. So because of that, there exists one more interaction where the lone pair of electron is involved in this kind of resonance. So here we are getting nitrogen loses electrons, so gets positive charge. There is a double bond between nitrogen and carbon. Carbon is singly bonded with the oxygen with the negative charge, and CH3. So like this, there exists another resonance structure of this manner. So the lone pair of electron is not only available for donation in the benzene ring, but also it is available for this kind of resonance. And that's why the activity of NH2 group is bit reduced. And this acylation or conversion of amino group into the acyl group, or introduction of acyl group into the amino group, this kind of process is considered as, or we call this as, protection of amino group. We are calling it as protection of amino group. Okay, and at the end of the reaction, we can get back the amino group by the hydrolysis of NHCOCH3. And acylation is done by using acetyl chloride in pyridine or acetic anhydride in pyridine. The reactions you have already studied. So by that we are converting it into, we are introducing the acyl group in the amino group so that the activity is reduced to get mono-substituted products. The first example of electrophilic substitution reaction is bromination. When aniline is reacted with bromine water at room temperature, it gives 2,4,6 tribromo aniline. As I said, when we are taking aniline, it gives a tribromo or tri-substituted anilines as a product. So here, when aniline is treated with bromine water, when it is treated with bromine water, what happens? The electrophile generated here is Br plus, bromonium ion, which goes and attacks ortho and para position. As we are taking here aniline, we are getting tribromo, tri-substituted aniline as a product. So the product formed here is tribromo aniline. This is 2,4,6 tribromoaniline. 2,4,6 tribromoaniline plus, as 1 hydrogen from all the 3 positions are removed, we are getting 3 moles of HBr as a byproduct. Okay, and this 2,4,6 tribromoaniline is a white color precipitate. On reaction of aniline with bromine water, we are getting white PPT, and that white PPT is because of the formation of 2,4,6 tribromoaniline. Okay. If you want mono-substituted aniline or mono-brominated aniline as a product, what we have to do is, we have to take aniline. Bromination is done only at one position. So for that, what we have to do, we have to take aniline. It is treated with, first it is treated with, to get the mono-substituted aniline, what we have to do, we have to protect this NH2 group. We have to reduce its activity by protecting NH2 group. So protection is done by acylation. So for acylation, what we have to take? We have to take acetic anhydride or acetyl chloride in pyridine. So when aniline is treated with acetic anhydride in pyridine, what we are getting? The acylation takes place. Here 1 hydrogen is replaced by COCH3. So we are getting NHCOCH3. So this compound is acetanilide. Common name of this compound is acetanilide. Okay, and specifically UPAC name will be N-phenyl ethanamide. Okay, so first we have to protect this NH2 group by acylation. Okay, so NHCOCH3. Now what we have to do? We have to do the bromination. Here bromination is done in presence of acetic acid, which is taken as a solvent. So bromine treated with acetanilide is treated with bromine in acetic acid, and this NHCOCH3 acyl group, this group is also ortho-para directing group. Compared to ortho, para will be the major product because of its stability. If we have ortho substitution, there will be a steric hindrance, so it will be less stable. So the major product will be para-bromo-acetanilide, as it is para directing. The bromination takes place at para position. It is ortho-para, but para is more stable. So this is the major product, para-bromo-acetanilide. Now we don't want acetanilide, we want aniline. So again we have to convert this NHCOCH3 into the NH2 group. So for that we have to do our hydrolysis, acid hydrolysis. What happens? There is a formation of aniline. Only this group is undergoing conversion. So there is a formation of 4-bromo or para-bromo aniline as a product. This is 4-bromo aniline. And you will be having the byproduct CH3COOH. Okay. So this is how the bromination is done for aniline. When we want mono-substituted mono-bromo-aniline, we have to follow this method. If we use directly bromine water at room temperature, we are getting tribromoaniline, 2,4,6 tribromoaniline as a product. If we want only single substituted aniline, then we have to follow this process. First, aniline is treated with acetic anhydride in presence of pyridine, which gives acetanilide, which is treated with bromine in acetic acid, forms para-bromo-acetanilide, which on hydrolysis gives para-bromo-aniline. Okay, para is the major product because of its stability. If it is at ortho, then there is a steric hindrance between these two groups. So we are getting para as a major product. The second example of electrophilic substitution reactions is nitration. For nitration, we are using nitrating mixture, that is a mixture of concentrated nitric acid and sulfuric acid. So when aniline is treated with a mixture of concentrated nitric acid and sulfuric acid at 288 Kelvin temperature. Nitric acid and sulfuric acid at 288 Kelvin temperature, we are getting nitration products. But here you should remember that the concentrated nitric acid is not only used for nitration, even it is a strong oxidizing agent. So whenever we use direct nitration, uncontrollable nitration, there is a possibility to get oxidation products also because of its oxidizing nature. So we have to control the whole process so that we have to get only the nitration products. So when this is subjected for controlled nitration, we are getting a mixture of ortho, para and meta-nitroanilines as a product. Like this, we are getting mixture of ortho, meta and para-nitroanilines as a product. Okay, here the para product will be, as it is very stable, we are getting in 51%, then meta will be 47% and 2% of orthonitroanilines. You observe here, we said that NH2 group is ortho-para directing group. So we are getting a mixture of, or we are getting the electrophiles, or electrophile gets attached to the ortho and para position. You observe here, we are getting meta-nitroaniline in 47%. So this unexpected amount of meta product is formed during this reaction. So this is because of the formation of anilinium ion, that is, as it is a strong acid and NH2 group is basic in nature. So because of that basic character, what happens? This aniline gets protonated and converts into NH3+. So because of the formation of anilinium ion, which is meta-directing, anilinium ion is meta-directing group. NH3 plus is meta-directing group, and for that reason we are getting unexpected more amount of meta product as a meta compound as a product in the nitration process. So like this, we are getting a mixture of nitro compounds by the nitration of aniline. So what we have to do to get only the single nitro compound as a major compound or single product or mono-substituted aniline, we have to again protect the NH2 group. So how that is done? The same reaction you have to take aniline, same process. First take the aniline, it is subjected for acylation, that is acidic treatment with acetic anhydride in pyridine. We are getting acetanilide. First step is same as that of bromination. We are getting acetanilide. Acetanilide is NHCOCH3. Now this acetanilide is subjected for nitration in presence of HNO3 and H2SO4 at 288 Kelvin temperature. So nitration takes place at para position. As NHCOCH3 is also ortho-para directing, because of the stability, para will be the major product. Even we get ortho, but it is in less amount. So we get para-nitroacetanilide. Now further this is treated with, it is subjected for hydrolysis, so that there is a formation of aniline. Para-nitroaniline is formed as a product, para-nitroaniline. Okay, so like this we get the major product, para-nitroaniline as a major product. So to get mono-substituted anilines, we have to first protect the NH2 group by doing acylation. Okay, I repeat, nitration of aniline results in the formation of mixture of para, meta and orthonitroanilines with some oxidation products. To get monosubstituted aniline, monosubstituted nitro compound of aniline, first aniline is treated with acetic anhydride in pyridine, it gives acetanilide. Then it is treated with nitrating mixture which gives para-nitroacetanilide, which on hydrolysis gives para-nitroaniline. The third electrophilic substitution reaction is sulfonation. For sulfonation, the reagent used is sulfuric acid, concentrated sulfuric acid. So, aniline is treated with sulfuric acid. Sulfuric acid is H2SO4. So to do the sulfonation, we are using here drastic condition. So easy, in spite of the presence of activating NH2 group also, it is not done so easily. So we have to use drastic conditions. In H2SO4, when it is treated with H2SO4, first there is a formation of a salt, that is anilinium hydrogen sulfate. As it is a strong acid and NH2 group is basic in nature, so what happens here, there is a presence of lone pair of electron. In H2SO4, you can just divide this H2SO4 as H plus and HSO4 minus. Okay, this is H2SO4. So what happens, this combines with the NH2 group. First, the lone pair of electron combines with H plus and there is a formation of NH3 plus. Like this, NH3 plus HSO4 minus. So like this, a salt is formed. This is called as anilinium hydrogen sulfate. Anilinium hydrogen sulfate. This on further heating at 453 to 473 Kelvin temperature. 453 to 473 Kelvin temperature with sulfuric acid, there is a formation of para-amino benzene sulfonic acid. When anilinium hydrogen sulfate is heated with sulfuric acid further at 453 to 473 Kelvin temperature, there is a formation of para-amino benzene. This is para-amino benzene sulfonic acid. Benzene sulfonic acid. Okay, this is commonly called as sulfonilic acid. This is commonly called as sulfonilic acid. Para-amino benzene sulfonic acid or sulfonilic acid. Okay, so this is formed, and here this is not present like this. Para-amino or sulfonilic acid is having both acidic as well as the basic group in it. So it is existing in the internal salt form. I'll write the same here. The product formed is this one. Okay, so this is present in the dipolar form. The dipolar form is the hydrogen from SO3H is taken by NH2 group and it forms NH3 plus. As it loses hydrogen, it forms SO3 minus. So like this, the internal salt is formed. The dipolar ion is formed, which is called as Zweiter ion. Because of it, this Zweiter ion formation, it is stabilized. Okay, I'll repeat the sulfonation of aniline. Aniline is treated with concentrated sulfuric acid. There is a formation of anilinium hydrogen sulfate, which on further heating with sulfuric acid at 453 to 473 Kelvin temperature gives para-amino benzene sulfonic acid, or commonly called as sulfonilic acid. It is the major product which is existing as a Zweiter ion, that is a dipolar ion, positive and the negative. Both the charges are present in the single species. So this dipolar ion is called as Zweiter ion. The fourth type of electrophilic substitution reaction is Friedel-Crafts reaction. Aromatic hydrocarbons are undergoing Friedel-Crafts reaction, and in this case aromatic hydrocarbons are usually treated with alkyl chloride. In the Friedel-Crafts reaction there are two types. One is Friedel-Crafts alkylation, another one is Friedel-Crafts acylation. During this reaction, what we are doing is the respective aromatic hydrocarbon. You may take any aromatic hydrocarbon. Here we are dealing with the aniline, so I will take here aniline. So aniline is treated with alkyl chloride. I will take here methyl chloride in presence of anhydrous AlCl3. Okay. In case of acylation, we are taking the aromatic hydrocarbon. Here we are taking aniline, and it is treated with acetyl chloride or acetic anhydride in presence of anhydrous AlCl3. So these are the reagents used in case of Friedel-Crafts reaction, that is alkyl halide in presence of anhydrous AlCl3 or acetyl chloride in presence of anhydrous AlCl3. So when we use these reagents, what happens? It is giving alkylated aromatic hydrocarbons. That is, here the CH3 group, in case of alkylation, CH3 group goes and attacks ortho or para position. And in case of acylation, acyl group, that is CO CH3 group, that goes and attacks the ortho and para position in case of aniline. But here, as we are taking anhydrous AlCl3, which is a Lewis acid. Anhydrous AlCl3, AlCl3 is a Lewis acid, whereas our aniline is a Lewis base. So as it is a Lewis base, what happens? The Lewis base and the Lewis acid, they combine to form a complex, and that's why whatever the required product, that is not formed in case of aniline. Friedel-Crafts reaction of aniline is not giving the required product. We are not getting alkylated aniline or acylated aniline. We are getting a complex formed by the combination of this Lewis base aniline and the Lewis acid aluminium chloride of this manner. That is, we are getting, as nitrogen is having lone pair of electron, it acts as a Lewis base. Those electrons it gives to the aluminium chloride as it accepts a lone pair of electron, and as it loses, it gets positive charge NH2 plus, and there is a formation of AlCl3 minus. So such complex is formed. Okay, so like this, there is a formation of a complex salt. So because of this particular reaction, whatever are required alkylated or acylated products are there, they are not formed. Okay, and this is because whatever the group we are getting here, this is highly electron withdrawing in nature, and because of its electron withdrawing nature, the electron density in the benzene ring will be reduced. This NH2 plus AlCl3 minus, whatever this complex is formed, this is highly strongly electron withdrawing in nature, and because of its electron withdrawing nature, it withdraws electrons from the benzene ring and makes it electron deficient. So as it becomes electron deficient, electrophilic substitution will not take place. As benzene ring is having more electrons, 6 pi electrons, it is electron rich center, that's why electrophilic substitution takes place. Now, because of the attachment of this group by the combination of NH2 and AlCl3, it gives an electron withdrawing group. It is this salt form is an electron withdrawing group which decreases the electron density in the benzene ring. So now the further reaction, whatever the expected Friedel-Crafts product is there, that is not formed. Okay, so that means, to sum up, what we can say, aniline is not undergoing Friedel-Crafts reaction because of the formation of the complex with aluminium chloride.